Hi everybody, we're going to start with chapter 4 of our textbook in quantum mechanics. We are looking at quantum mechanics in 3D now, so we're starting to get into some interesting stuff. So as we start, we're going to start with section 1 in chapter 4, which is the Schrodinger Equation in spherical coordinates. I'm going to go to pen and paper now, as it probably is going to be more legible than the touch screen of my laptop. So our Schrodinger in spherical coordinates is going to be IH bar, the time derivative of our wave equation, equal to the Hamiltonian acting on our wave equation. So we're going to start out with the Hamiltonian from classical energy. So our Hamiltonian, remember, has to do with energy. So from classical, we are going to have both our kinetic energy, so 1/2 mv squared, and whatever potential energy function we have. In terms of our functions that we've been using in our quantum mechanics, instead of writing our kinetic energy like this, the 1/2 mv squared, we're going to write it in terms of our momentum. So we're going to have a momentum in each direction, the x, the y, and the z direction with Cartesian. And then instead of 1/2 mv squared, we're going to have 1/2m times our momentum squared. That's going to be the same statement. And then, of course, whatever potential energy we have going on. So those p's are our momentum functions. All right, so in our work so far in quantum, we've written our momentum in terms of an operator, right? And that operator was h bar over I and a derivative. So now that we are in 3 dimensions, we're going to have a partial derivative in x, in y, and in z. So we are going to have momentum operators that look like this. Easy enough, right? So there is a footnote in your chapter 4 and onward that they've stopped using the hats for operators. So even though we were using hats for operators, it's gonna disappear from your textbook at this point. I'm not sure why. I guess it's just saving ink, whatever. So in other words, if we take these 3 things together, our momentum operator looks like h bar over I and our del operator, right? So our Schrodinger can be rewritten as IH bar, get myself on the screen, IH bar, our partial derivative with respect to time of our wave function, and then h bar squared over 2m del squared momentum, right? So we can write it in terms of our del operator. Now that del squared, you might remember from a previous class, is just taking a second derivative, right? So that partial derivative. So that's an instruction to do something to the item following it. In this case, the wave equation following that instruction. So that's the Laplacian in Cartesian, if we want to be technical. So the Laplacian in Cartesian coordinates. And again, that V is your potential energy. Your wave function, of course, is just a function. And all of these can be functions. So we could write both of these of a position. So that position we could describe with our Cartesian coordinates, and a function of time, right? If we want to talk about the probability of finding a particle in a certain place. So if we want to talk, let's start numbering my pages. If we want to talk about the probability of finding a particle, not just at a point in space, but now in a volume of space. So going to 3 dimensions, we get to go to volumes. So we would say that volume we could call D3R, which we could just define as a little bit of X, a little bit of Y, a little bit of Z, right? So that's our little volume here, right? That probability is going to be given in kind of the same way we found it in 1 dimension. Again, our wave function is now a function of 3 different dimensions and t. And that probability of finding this, we're going to take, oops, I don't want that integral yet. We're going to take our magnitude of that wave function squared and that volume. So our wave function is going to give us some information about where we are likely to find a particle. Our normalization then in 3D looks like, this is where we want the integral, our wave function. And again, that's a function of all 3 dimensions of space and then also time. It's going to look like the magnitude of that squared integrated over that whole volume. And we would do this integral from in all the space that this is likely to exist. And then our probability should be 1 or 100%. So that integral is over all space, or over all space where this wave function is known to exist. So in 3 dimensions, we can also come up with a complete set of stationary states. Again, that would be if our potential is time independent. So our complete set of stationary states looks like our psi to the n, right? So we've got the nth state, right? Again, function of space and time. And it is going to be a function of just space, and then our time-dependent portion, just like it was in a single dimension, is going to have a time dependency that is based on allowed energies and some of our constants there. Okay, so again, this is our spatial wave function that satisfies the time-independent Schrodinger wave equation. So we could write that that spatial wave function satisfies our time-independent Schrodinger equation, which our time-independent Schrodinger equation should look like this. Yes? Okay, so our general solution to the time-dependent equation is going to be our wave function that is dependent on both time and space. And it's going to be given by those coefficients that tell us what contribution each of these stationary states has to the overall time-dependent equation, and then or time-dependent part of it. Those CNs, again, are those constants determined by the initial wave functions. If we've got a continuous state, this summation is just going to go to an integral for those continuous states. So this is kind of review of what we already did in the one-dimensional case. We're just now applying it to 3 dimensions. Okay, so we want to get into talking about this in spherical coordinates. So far I've said something about Cartesian, and then we've kind of thrown an R in there, but we haven't really talked about this in spherical coordinates quite yet. So we need to define some spherical coordinates. Let me get my paper moved so that we have a little more space. So our spherical coordinates we're going to talk about spherical coordinates when our potential is a function of distance from the origin. This makes a lot of sense in something like, say, the hydrogen atom, where our potential is a function, or our potential for an electron is a function of our distance from our proton in the middle of the hydrogen atom. Okay, so function of the distance from the origin. We are going to talk about spherical in terms of R, in terms of theta, and in terms of phi. So how did we define R, theta, and phi? So in Cartesian, I have my X and my Y and my Z. I'm going to grab some different colored pens here if I can. If I want to talk about a point out in space, I might first go on the XY axis and measure a certain distance out that is phi. Then I'm going to go up to that point. I'm going to measure a certain distance from the Z-axis that is theta. And this distance out here from the origin, that length is R. So theta is my distance down from the Z-axis. Phi is my distance around clockwise towards the positive Y-axis from the positive X-axis. And R is my distance out to that point from the origin. Okay, so once we are in our spherical coordinates, we need to then define these things that we've already used, for our Schrodinger wave equation. So one of the things that we've already used is our Laplacian. Right, so our Laplacian in Cartesian coordinates was pretty easy, but our Laplacian in spherical coordinates, and this can be derived, it's a pretty, I don't know, satisfying derivation if you're into derivations. But it's also in the front cover of many of your textbooks. So I have a cat that's trying to interrupt my lecture. Let me move her out of the way. Okay, so your Laplacian in spherical looks like this for our first term, for our term, then 1 over r squared sine theta d theta sine theta d theta. And then finally our third term, 1 over r squared sine squared theta. And then an instruction for 2 of these derivatives. So this instruction is really for each of these terms. For instance, you would apply the first derivative with respect to theta then multiply that result times sine theta, then apply another derivative with respect to theta, then do this. So when you're applying the Laplacian, you work from right to left with all these instructions to do these derivatives and multiply towards these things. You can picture that taking two derivatives with respect to r and then applying this r squared would give you a very different answer than doing it in the order it's listed here. So order matters here. Okay, so then if that's our Laplacian in spherical, we have also our time-independent Schrodinger equation. There goes a cat. That's a furry little beast. All right, back to work. So, time-independent Schrodinger in our spherical coordinates. That's where we were before we were interrupted by pets. Okay, get my lighting rearranged. So our time-independent Schrodinger in spherical gets a little messier looking than what we had in Cartesian because we have to include this Laplacian up here. So I've got 1 over r squared, an instruction to take a derivative, another instruction to take a derivative. Okay, I'm going to copy what's above down in here where the Laplacian is. Okay, so there's our 3 dimensions. So that is negative h bar squared over 2m, our Laplacian in spherical, that isn't even all of it, then plus v, so our potential, whatever that may be, times and we need our wave function there. So plus v times our wave function, and that should equal energy and our wave function. Fun and exciting. So what we want to do for this Schrodinger equation is we want to look for solutions that are separable. And by that, I mean separable into products. So we want to look for solutions that are functions of each of these things individually. So we're going to look for solutions that look like a radial function that's only a function of r. And we're going to go with an angular function that is a function of theta and phi. And then we're going to further separate this angular function into its own 2 things, right? So what you're going to do is you're going to take this test equation, we'll call it. You're going to put that into the Schrodinger equation up here. You're going to take lots of derivatives, right? So if we take a derivative of this with respect to r, we're only going to get out this portion, right? And we're treating this as a constant. You may or may not have done this already in Quantum 1. It's kind of a fun exercise. It is really, really messy. Once you have all those derivatives taken, you are gonna put them in there and move things around to separate, right? So hence the idea of separable solutions. So you're gonna separate terms, and this equation, you're going to collect all of the radial things together. So that r, again, is that function, our radial function, something that's only a function of r. So I'm going to separate all my terms we are going to work with the assumption that our potential is only a function of R as well. So like our Coulomb potential for our hydrogen atom is where we're headed. So we have this stuff for our radial part of the equation. Then we've got another set of things for our angular parts of the equation. These I am leaving the derivatives as partial derivatives since we have both theta and phi in our radial or our angular part of the equation. All right, so that is a very long equation, 2 lines worth of it, but we've separated things into a radial and an angular part of thing. So this one up here in these brackets depends on R only, depends on the radial variable only, and this one depends on theta and phi only. If that's the case, our differential equations, our tricks with differential equations, lets us say that both sides, both terms, let's go with terms, must be a constant. Because if we can change R without changing theta or phi and still have this be true, still have it be equal to 0, that means both of these things have to be constants. So what we're going to do is we're going to take the things in that top bracket. So I'm going to be kind of lazy and I'm just going to call it the R bracket. And we're going to set that R bracket equal to a constant. Now, this doesn't look like a simple constant, but there's a reason for picking L plus or times L plus 1, right? So that'll make solving this differential equation a little bit easier. And then our angular bracket, so that's my theta and my phi. Okay, if adding this to the R bracket gives us 0, we gotta say our angular bracket is equal to minus L times the quantity L plus 1. Okay, on to another page. Let's get another page going here. Okay, so our bracket is gonna determine a radial dependence, and our angular bracket is gonna determine the dependence of psi on theta and phi. So we're going to start with that angular equation actually. So this bracket that I had that has theta and phi terms in it that I said was equal to minus L plus 1. I'm going to take that and I'm going to multiply by my function that I'm trying to solve for and sine squared theta. Now, if you look at the bracket that we already wrote, so let's go back to that. If we look at this, what's going to happen when I multiply by our function and by a sine squared theta? I'm just going to get rid of some of these fractions on the one side. So when I do that, what I have is a sine theta, an instruction to take a derivative, another sine theta, an instruction to take a derivative, okay, so I have something that looks like that. That is actually the same equation as in the solution to Laplace's equation in classical electrodynamics. So you guys have seen this in your electrodynamics course, right? So if that's the same solution, we don't really need to reinvent the wheel. We can just dive in and find that solution. So that solution for that equation, something that would work, is something that is also separable. So we're going to separate further, just like I said, into something that is a function of theta and something that is a function of phi. So my capital theta looks, I don't know, like some sort of spaceship, but trying to distinguish between my lowercase theta and my capital theta there. So that's the same solution. We're going to do a separation of variables here. Again, right? Okay, so we're going to plug that into the differential equation above. That's how we do separation of variables. We take this, plug it into this equation right here, and rearrange to separate things. So plug in, rearrange, and separate. All right, so when I do that, I have my function, again, trying to distinguish my function from my variable. I have sign of my variable. We can go to ordinary derivatives since we're separating. Take a derivative of my function with respect to my variable. Some brackets. Okay, so that's all the things that are theta dependent. Again, since we can separate them, I'm going to set that equal to a constant. Then all our things that are phi dependent look like a pretty simple statement. So second derivative there, and we're going to set it equal to the opposite constant, right? Because if those two things added together give us 0, they should be equal and opposite. Okay, so the first one I want to attack is actually my phi equation because it looks like the simplest thing to attack. So the phi equation, if we rearrange that just a little bit, it says the second derivative of the phi equation equals negative a constant squared times our original equation. That's a pretty simple differential equation for us to solve, right? The general solution would be e to the I m phi, right? In this case, our m can be a positive or a negative number. It doesn't matter. But since we are in spherical coordinates, we do have a boundary condition. So for our phi equation, we would require that it is continuous when we hit the point where we circle back around, right? So we would have this requirement. So in that case, you are saying that e to the 2 pi I m should equal e to the 0, right, or 1. And so m has to be an integer. So 0 plus or minus 1 plus or minus 2 and so on. M has to be an integer value. And so that comes from that requirement of being continuous at the boundary. And we can get to this statement from Euler's equation. Okay, so that's our solution to our phi equation. Now, what about our other angular equation? So our other angular equation is the theta equation, which I've got right here. So let's do that. So our theta equation is not so easy to solve, but we don't have to. Our theta equation is actually something, again, we saw in electrodynamics, where we are going to need Legendre functions. So we are going to look at these functions. So they're denoted by our m and our l. So those are the values that we've already used as our constants here. There are entire tables of these functions, and there are tables to be found in your book. But these are the theta angular equations that are a little more complex than the phi angular equations. So your equation is going to have an argument x. Here we've got as our argument cosine theta. So where you see x, you're going to put in a cosine theta. So in general, the definition looks like this. So a derivative with respect to x, m number of times, 1 minus x squared to the m number of times over 2. And then our function, right? And so that thing is the nth polynomial. Again, entire tables of this. And that is the nth polynomial defined by something called the Rodriguez formula. So the Rodriguez formula looks like P sub L to the X 1 over 2 to the L, and then L factorial d dx, do that L number of times, on x squared minus 1 to the L power, right? So L must be a non-negative integer. So we start at 1 or 0, 1, 2. M can be anything from negative L, right, all the way up to L, right? So there are 2L plus 1, because plus 0, possible values of M. There are other solutions that exist, but they are unacceptable with the boundary condition. All right, so that is a good place to pause right now. We'll pick up with this in the next video.